The one team just did something wild. They stuck an AI chip inside a furnace so hot your laptop would liquefy in seconds, about 1300 degrees Fahrenheit, 700 Celsius, and then let it run for weeks. It didn't even sweat. Hey, I'm Bizbor, and today we're stepping right into that blast furnace to ask a simple question. What changes when AI no longer cares about overheating? Here's the thing. This little chip doesn't dodge the heat, it embraces it. Imagine an athlete who actually gets stronger the harder you push them. As the temperature climbs, the chip's oxide layers reshuffle their atoms into an even sturdier order, so the math keeps flowing. It's weird for two big reasons. First, brain and notebook are the same spot. The calculation and the memory share a microscopic patch of oxide, no separate RAM, no long metal highways. Second, the materials aren't exotic. We're talking low-cost oxides you can already buy by the barrel, not some unobtainium grown on Mars. Put those two facts together and you unlock AI that lives directly in the harsh zone. Turbines, reactors, even rocket nozzles. No cable back to an air-conditioned data center. The smarts sit right where the action is. Let's paint a picture. Imagine designing the next generation of machines around this idea, not bolting it on later. A turbine blade could host thousands of these cells, tiny math coprocessors listening to temperature and vibration, making micro-adjustments in real time. No round trip to the cloud, no precious milliseconds lost. Feels like science fiction, right? But the architecture makes it possible. Traditional chips separate calculation and storage. Data shuttles back and forth, wasting energy and generating heat we then have to remove. With this oxide stack, the place that holds a number can immediately multiply it by something else. Those famous weights times inputs in neural nets, right on the spot. That local negotiation slashes traffic and, bonus, loves the heat. Shift your mental model. Instead of one giant, fragile brain that must stay cool, we get swarms of rugged mini-brains that thrive on heat and fit anywhere. Let that sink in for a second. Now, about failure. Classic electronics have a hard cutoff. Past 100 degrees Celsius, game over. Our new friend behaves more like a spring. Stress it, cool it, electrically exercise it, and it bounces back. A control system could literally work out its own memory blocks after a thermal spike, maintenance by self-care instead of a service call. Because each element is cheap and tiny, the bigger shakeup might be economic. If we can embed thousands of these cells like sprinkles inside equipment that's currently blind to its own extremes, then high-temperature AI turns from boutique add-on to commodity. Intelligence becomes a material property, like insulation or rust-proofing. Picture a jet engine. Today it just reports, "Hey, I'm hot." Tomorrow, embedded AI experiments with a micro-tweak to the fuel mix, compares it to patterns from 1,000 earlier flights, and settles on the sweet spot before a human even notices. Or think of a geothermal drill. It senses a vibration signature that once led to a fracture, eases torque automatically, and saves the entire drill string. No dashboard, no human reflexes, just instant judgment in the hole. There's another benefit: black box transparency. In hostile zones, we usually lose logs. Here, the learning and the storage happen on site, so you can replay exactly what the engine saw during a near miss. Troubleshooting gets a crystal clear window. And that brings culture into play. Engineers start seeing the hottest part of a system as the smartest part. Accountability shifts. Regulators will want tamper-proof logs. Think flight recorders that live in magma. Workers become supervisors of embedded judgment rather than direct operators. It raises new questions about trust and liability. Who signs off when code you can't physically reach rewrites its own strategy? If this vision lands, heat-tolerant AI becomes as ordinary as concrete. We might someday certify skyscrapers not just for fire resistance, but for how wisely their embedded systems behave while the building is literally on fire. So, where does that leave you? Before we wrap, I've got 3 prompts for your brain. 1. If chips that shrug off 1300-degree heat were on the shelf tomorrow, where in your world, workshop, factory floor, hobby lab, would you stick one? What real-time decision could it take off your plate? 2. What new data streams would suddenly matter? In-engine vibration, kiln atmosphere, downhole telemetry. Pick one and start mapping where that data already lives. 3. If you had to pitch a single heat-proof AI idea to your boss or a friend, what would it be? And what's the next baby step to test if the parts and permissions line up? Alright, let's land this plane. So here's what we covered today. First, researchers fired up a tiny oxide-based chip at 1300 degrees Fahrenheit and proved it can run AI for weeks without breaking a sweat. Second, the magic lies in a material that combines memory and calculation in the same spot, loves heat, and costs pennies. Third, that opens the door to distributed mini-brains living right inside turbines, drills, and rockets, making split-second calls no cloud could match. Self-healing under stress flips our whole idea of failure and maintenance. And finally, once intelligence lives in the furnace, accountability, regulation, and even job roles will have to move there too. Here's the empowering bit. You don't have to wait for a billion-dollar factory. The materials are already on the market, and the use cases are limited only by your imagination. So this week, scout your own hot zone. Ask, what could an on-site AI decide faster and smarter than any remote server? Then take one concrete step toward that future, even if it's just jotting the idea on a sticky note. Because the next wave of AI won't need air conditioning. It'll be born in the fire. And if you're ready, your project could be there with it. Stay curious, stay cool, or in this case, stay hot, and I'll catch you next time.